Okay, so in this lesson, it's called Lesson 2, Writing Products as Sums and Sums as Products. So sums are addition, products are multiplication. So we're going to be going back and forth between some addition and multiplication again. And the big deal for this lesson is we're going to find out what a tape diagram is. Now, you guys used this in everyday math when you were in elementary school. You did tape diagrams, so I'll remind you what those are. But those can really be helpful sometimes when we're writing expressions and then trying to figure out some ways to simplify those or rewrite those. So with this first one, let's just take a look and see what the situation is. It says solve the problem using a tape diagram. A sum of money was shared between George and Benjamin in a ratio, okay, getting into ratios, we did this earlier this year, of 3 to 4. If the sum of money was $56, how much did George get? All right, so this is going to be really important, this ratio right here, 3 to 4. And it says it was shared between George and Benjamin in a ratio of 3 to 4, so that order matters. That means George had this 3, and Benjamin's was the 4. George to Benjamin, 3 to 4 right there. So that means for every 3 pieces that George had, Benjamin had 4 pieces, essentially. Or 3 things of money George had, Benjamin had 4 of those money. So if we look at this as they each just have 1, I'm going to wait for our buzzing here. Okay, sorry guys, I had to pause for our tornado drill. So let me go back to what I was saying about if there are 3 for George and 4 for Benjamin, let's assume they each have just, George has 3 and Benjamin has 4. So how many total pieces of money would we have here? 3 plus 4 would be 7. Let's just try and draw that out. George and Benjamin. We don't know how much is in this piece of money here, but George has 3 of them, and we're going to make what you guys used to use for tape diagrams. George has 3 pieces, and Benjamin has those same 3 pieces, but he also has a 4th piece of the money. So we've got a total of 7 pieces. Right? So since the total money was $56, right? Total of 7 pieces, and that equaled $56. How many must be in each piece? Well, what's 56 divided by 7 pieces? Would be 8. So in each of these pieces, it must be worth $8. $8, $8, and $8. All of these pieces are each going to be worth $8. So how much money did George have? How much money did Benjamin have? What's 8 times 3? 24. And Benjamin would have had 8 times 4, which would be 32. So the question actually asks us, let's see, how much did George get? He got $24. So in this situation, we used the tape diagram, these pieces that we didn't know how much they were, to help us work backwards and figure out this problem. So we're going to show you how you can use tape diagrams for a couple of other things too, and some of these are super quick. If we just wanted to represent 3 plus 2 using a tape diagram, well, you'd have 3 pieces of tape, and you'd add on 2 pieces of tape, and you'd have 3 here plus 2 here. And what would 3 plus 2 be? That would equal 5. Right? That would be our simplified expression for that one. So what if, though, we have variables? If we have x plus 2. So here's what we usually do. We usually use a little bit of a longer piece of tape and call that x. So if we've got x plus 2, then you could use a smaller one for each of these ones, essentially. X plus 1, 2, that tape diagram would represent x plus 2. So anytime we use an x, we'll just have the variable, and any x's we used in there would all be the same length, even though we don't exactly know how much x is. So let's try this one. Represent x plus x plus x plus y plus y plus y using a tape diagram. Well, all right. So we can use x, and it really doesn't matter how long it is, but we want our next x to be about the same length to show that they're the same value. So there would be our x plus x plus x. And then maybe we make our y's just about, I don't know, shorter than that. You want to make our y's like this. We don't really know how much y is, but we want it to look a little bit different than x. So plus a y, plus a y, plus a y, just to show that all the x's are the same and all the y's are the same, but they don't necessarily have to be the same amounts. They could, we just don't know. So there would be x plus x plus x, plus then a y plus y plus y. So how would we represent 3x plus 3y? All right, now this is multiplication. Up here we had addition. Isn't 3x the same thing as x plus x plus x? And 3y is the same as y plus y plus y? We're writing a product as a sum, or a sum, addition, as a product. And we want to show that it is the same thing. So here, wouldn't it literally look exactly the same as that? 3x's plus 3y's lined up? It would be exactly the same. What about this guy? X plus y plus x plus y plus x plus y. Okay, so let's try and draw this one. If I can keep my x about the same length that it was before. Here's my x plus a y, and my y was a little bit smaller. That would be an x plus a y. And then I'm going to do another x plus a y plus another x plus a y. So in there, do I have 3 x's and 3 y's? Up here, did I have 3 x's and 3 y's? Yeah. And if I actually drew these the right length, that x looks a little short to me right there. If I drew them the right length, it should be the same length as that one up there, because there's still 3 x's and 3 y's, they're just in a different place. So I'm going to put up there, it would be the same length. It would be the same exact expression, just in a different order. Right? What about this guy? 3x plus y's. 3x plus y's. Well, if there's 3x plus y's, this is 1x plus y, this is 2x plus y, this is 3x plus y's. So it would be the same as that. Or could we think about this as the distributive property? 3x plus 3y. And then we have what was up there already. So we have just proved, essentially using this tape diagram that's all the same length, that 3x plus y, x plus y plus x plus y plus x plus y, 3x plus 3y, x plus x plus x plus y plus y plus y, all 4 of those are equivalent expressions because their tape diagram would be the same length. You've got the same things in them. All right, so we're looking at equivalent expressions, but we're also learning to use these tape diagrams to be able to help us figure some things out. So let's look at one more way that we can use tape diagrams. I'm going to flip this over. And the tape diagrams can be used to make this thing called a rectangular array, which is just a bunch of tape diagrams stacked on top of each other to make a rectangle. So find an equivalent expression by modeling with a rectangular array, I'll show you that, and applying the distributive property. So this first expression says 3 times 4x plus 3. All right, this is a multiplication problem, but we're also going to use this to make a rectangle. And this number out in front tells us how many rows to make. You guys have made rectangular arrays before when you were learning how to multiply originally. How many rows, and then what it's multiplied by, that second thing, that second part of the multiplication problem, is how many columns. That's what's in the columns, essentially. So this is the number of rows. All right. Let me show you what this looks like to draw it. It means that there are 3 rows of, because of is multiplication, right? 3 rows of 4x plus 3. I think I said that wrong before. The 4x plus 3 is what's in the row. It makes up the column. You'll see here. There's 3 rows. I'm going to make 3 rows. I'm going to have 3 of those. 1, 2, 3. And I'm going to put a top on it, essentially. 3 rows. And in each row, I'm going to have 4x plus 3 in each row. So I need 4x, and I'm going to write plus 3 up at the top. So I need 4 x's in each row. Well, here would be, I'm going to make an x, an x, an x, and an x. There's 4 x's. And then I need just 3 ones. So 1, 2, 3, 1, 1, 1. Does that give me 4x plus 3? So I have one 4x plus 3 there. If I make another row, I'm going to have two 4x's plus 3. And if I make a third row, I'm going to have 1, 2, 3 4x's plus 3's. So when I do that, what it shows us is just a representation of the distributive property using an area model. And I know you guys did this in everyday math. So 3 times 4x plus 3, how many x's would I have? I'm going to make a better boundary between my x's and my 1's. How many x's would I have total? I'd have 4 and then 3 rows of that. 4 times 3, I'd have 12 x's total. How many 1's would I have? Well, I have 3 and then 3 rows of that. 3 times 3 is 9. This shows us the visual representation of the distributive property that you could literally count your x's and your 1's, and it would show you 3 times 4x and 3 times 3, and show you that distributive property. So when you're making these, you can either fill in all of these x's on there, or you can at least write the top row and show me what it would be with blank spaces at the bottom. So we'll do a little more practice and I'll show you. Can you try and draw a rectangular array for 3 and then 3 plus 2? Okay, this one has no variables. So 3 rows, that's our number of rows, and each row is going to have 3 plus 2 in it. So if I made a 3 plus 2, 3 plus 2, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I made that a little too long at the end. Isn't that 3 plus 2? It's really just 5 in there, right? But I need 3 rows of it. So I want to have 2 more rows, and I can just extend my little dividing line down here. 3 rows of 3 plus 2, kind of a dividing line. So what would I have if I used the distributive property? How many of these ones would I have? 3 times 3 is 9. 3 times 2 is 6. I'd have 6 on this side. I'd have 9 plus 6. And if I counted every single one of those, how many would I have total? I would just have 15. Just like saying 3 times 5. So that was a basic one. We probably wouldn't do that very often because it didn't have any variables on there. Let's try one with variables. Draw a rectangular array for 3 and then x plus 2. So I'm going to make, this is going to be my number of rows. I'm going to make my x plus 2 first. Here's my x, let's say, and then I'm going to stick 2 more 1's on the end there. Make that a little long. And I want 3 rows of that. There we go, 3 rows. I'm going to put my 3 here, 3 rows of x plus 2. And to find the area, everything that's in there, I would do length times width. 3 times x plus 2, which is just what this is right here. And this proves to us that it's 3 times x and 3 times 2, because 3 times x would give us, how many x's would there be total? 3 times x. There's 3 x's total. 3 times 2 over here would be 6 1's total. And if we count them, that's how much is in there. That's the area of that rectangle. So the area of this whole rectangle right here is 3 times x plus 2, 3x plus 6. There is our equivalent expression. So that's our rectangular array that goes along with this one. All right, I'm actually going to change this one up a little bit. Will you guys change this one with me? We're going to draw one for 3 parentheses 3x plus 4. I'm going to make more x's in here. So 3 rows again, but in each row I'm going to have 3 x's. So I'll do that first. X, oh, that's a little bit short. Not perfect size x's. 3 x's plus 1, 2, 3, 4. There's my 3x plus 4. And how many rows do I need? 3 rows total. You can see that I am not the best at spacing this out, so you don't have to be perfect on it. Just do the best you can to make them similar lengths. So if I put my numbers, that's my 3 rows of, here's my 3 x's, plus, over here's my 4. So how many of everything do I have? Over here I have 3 times 3x, which would be 9 x's. Would there be 9 x's if I filled in all those boxes? Yeah. An area model, length times width, 3 times 4 is 12. Would there be 12 1's if I filled all that in? Absolutely. All right, So would we be able to draw an array for this one? 5 times 2c plus 5. Let's just give it a try. This is my number of rows. So in each row, there's going to be 2 c's. You can be the same as your x. It's a whole different problem. So however long you want c to be, plus 1, 2, 3, 4, 5. There's my 2 c's plus 5. And how many rows do I need? 5 rows. There's what, second, third, fourth, fifth on there. So it's okay if you don't want to fill in all the 1's and c's, but we can just make it look like they're going to be there. And how many rows were there? 5. So how many of everything is going to be in there now? There's going to be 5 rows of 2 c's, which would be 10 c's, plus 5 rows of 5, which would be 25. If you counted all those 1's, there's literally going to be 25 1's in there. So here's our rectangular array for it. Let me just show you one last rectangular array here with negatives on here, because this -1 is really a plus -1. So how would we draw a picture if we had a negative in there? Well, this one's 3, so still 3 rows of 4f plus -1. Here's how I would do that. I'm going to call my f, however long I want that to be. F, there's 4 f's. And then if I have a -1, I'm just going to make a regular box like I would a 1, but instead I'm just going to put like a negative in there, and then I'll know it's a -1. And then I'd want 3 rows of that. So there's 3 rows of 4 f's, and then over here plus my -1 that's there. 3 4f's would be how many f's? If we counted all of these, there would be 12 f's, plus 3 of these -1's would be -3. So that would be our distributive property, 3 times 4f and 3 times -1. So we're going to ask you to be able to draw these rectangular arrays also on your own, just to show us that distributive property is also representing this idea of this area model. And you guys have done that before, just to show visually that this is equivalent to this right here. All right, we're going to be done with this video, and we'll move on to the next thing.